This diagram illustrates an X-ray tube, which is essentially a high-voltage crash zone. When highly accelerated electrons smash into a target wall, they produce exactly one thing: a tiny fraction of X-ray photons alongside a massive, radiating burst of pure thermal energy. To safely harness this reaction, we need three basic elements: an electron source, a target, and an evacuated, shielded container. Here, that container is a Pyrex glass envelope encased in a lead-lined housing and filled with cooling oil. Because 99% of the energy from that subatomic collision turns into heat, every major engineering decision inside this tube is a thermal management strategy. Looking at the left side of our blueprint, we find the cathode, our negative terminal. It acts as our electron source through a process called thermionic emission, which uses electrical current to boil electrons off a wire. The material choices here are highly specific. The wire filament is made of tungsten to withstand that extreme boiling heat without melting. Surrounding it is a focusing cup made of molybdenum. Because molybdenum is negatively charged, it forces the mutually repelling electrons to group tightly together. The cathode provides a perfectly grouped, high-capacity ammunition supply of electrons, prepped and ready to fire. To pull the trigger, we apply the tube voltage, or kVp. This creates a massive electrical gradient that acts like a whip, accelerating our group of electrons across the vacuum to smash into the positive side of the tube, the anode. This schematic focuses on the target they strike, a stationary anode. It relies on a dual material design, a small tungsten button placed exactly at the point of impact to produce the X-rays, embedded deeply within a thick, solid copper stem. Upon impact, the materials divide the labor. The resulting X-ray photons beam down and out through the glass window, while the extreme thermal energy conducts directly down the copper stem to disperse into the surrounding oil. This stationary design is highly effective for quick, low-power scans, like dental imaging. However, the system hits a thermal bottleneck the moment a scan requires the deep anatomical penetration of a human abdomen. This photograph shows the face of a physical anode disc. Look at the wear and pitting along the track. This is what happens to a tiny stationary spot of tungsten when it takes the sustained heat required for a heavy-duty scan. To solve this melting problem, engineers replaced the stationary copper stem with a rotating anode. It consists of a spinning tungsten rhenium disc powered by an external induction motor containing a stator and rotor. By spinning the disc, the incoming electron beam no longer strikes a single point. Instead, it hits a continuously moving focal track. This geometry spreads the same immense heat load over a massive circular surface area. This high-speed rotation serves as the ultimate thermal defense, providing the endurance required for high-power, long-duration medical imaging. This image contrasts the rotating anode's cross-section diagram with the actual physical rotor and disc assembly. While stationary anodes remain standard for low-dose work, this rotating design is required for heavy-duty, high-dose scans like fluoroscopy. Returning to our complete schematic, we have the cathode generating electrons and the anode target receiving the impact, all safely housed within the Pyrex envelope. Across all designs, the defining rule remains: diagnostic capability is strictly bound by the capacity to disperse thermal energy. Mastering these components reveals how engineering safely captures subatomic physics for medical discovery.